Okay, guys, so this is we're going to talk about isotopes and atomic mass on this lesson. So I've gone ahead and I've drawn, these are nuclei. They're not very good, but you get the idea. So here's a nucleus of an atom and the nucleus of another atom. The electrons don't really matter as far as this is concerned. And so the blue dots represent protons and the green dots represent neutrons. And so if you look in this atom, we have 1, 2, 3, 4, 5, 6 blue dots. So we have 6 protons. We have 1, 2, 3, 4, 5, 6 green dots. So we have 6 neutrons. If you look at this other atom over here, we have 1, 2, 3, 4, 5, 6 protons. And we have 1, 2, 3, 4, 5, 6, 7, 8 neutrons. And so here's the thing. They both have 6 protons. And what did we learn about protons? Protons is the atomic number, and the atomic number identifies what the element is. And so 6 protons make both of these carbon. This is carbon 12 because it's got a mass number of 12. 6 plus 6 is 12. This is carbon 14. 6 plus 8 is 14. Now, they are both carbon. In every sense of the word, they are carbon. They both would normally have 6 electrons. The number of protons and the number of electrons are what determine the chemical properties. So protons and electrons determine chemical properties. And so in every way, they are going to behave as carbon in any kind of chemical reaction. They are different in the fact that they have different numbers of neutrons. That makes their masses different. One thing about these two elements, or these two isotopes, these are called isotopes, is that the carbon 14 is radioactive, the carbon 12 is not. And so that is one way in which these are different. These are called isotopes. An isotope, or isotopes, are 2 or more atoms of the same element that have different numbers of neutrons. Now, if their neutrons are different, that also gives them different mass numbers. And those are isotopes. Again, in every chemical way, as far as chemical reactions is concerned, they're going to be the same. They're going to behave the same in any kind of chemical reaction. They are slightly different in their masses. Sometimes some isotopes are radioactive and others are not, but that's not chemical, that's nuclear reactions or nuclear decays, and so they are chemically identical. What that does, however, though, is you need to look at isotopes to calculate atomic masses. And so today we're going to be looking at atomic masses. An atomic mass is the weighted average of all isotopes of an element. And so on the periodic table, you have those two numbers on each element tile. The atomic number, which for carbon would be 6, and you have the atomic mass, which for carbon would be 12.011. And the atomic mass is this weighted average. And we're talking about weighted here in just a second. You take basically the carbon in the universe and you take a sample of it and you take a weight and divide it by the number of atoms, and then you get the weighted average. And that's what you get. So let's talk about a weighted average here for a second, because I think it's important you understand what that is. Now, grades, your grades are weighted averages. For example, in our class, this is a little simplistic, but it's basically what it is. You have a 70% split and a 30% split. And we can, for simplistically, we can say it's 70% major grades. So those are going to be mostly our tests and our formal lab reports and projects and things like that. And 30% of your grade will come from what we can call minor grades, although this is not technically how it is. It's close enough. So minor grades might be your quizzes, your homeworks, informal labs, lab activities, things like that. And so your grade is weighted differently for these two categories. And let's say you had a 90 in your test average and you had a 70 in your homework average. What would your average be? Well, it wouldn't be halfway between these two. It would not be an 80 because the major grades are weighted heavier than the minor grades. And so the way that you would calculate this out is you would take your grade 90 times the percent of your grade 0.7 and add it to the other category 70 times its percent 0.3, and this would give you your basically your weighted grade. And so 90 times 0.7 would give you 63. 70 times 0.3 would give you 21. Add those two together, you're going to get 84. And you can see instead of being in the middle at 80, we are weighted to an 84 because major grades are more important. And so this is exactly how atomic masses work. You're going to simply weight based on the percentage by the mass, and we're going to figure it out. So let's get a basic formula that we can use to do so. Now, since it's atomic mass is the weighted mass, we're going to look at the mass of isotope 1 times the percent abundance is what we're going to call it of isotope 1, and we're going to add to that the mass of isotope 2 times the percent abundance of isotope 2. And we can go on and on here, however many isotopes we have. So we can go dot, dot, dot. If we have 3 isotopes, we'll add a plus 3. If we had 4, we'll add a plus 4. And when you add all those up, you'll get the atomic mass of an element. Okay? And so this, we can shorthand that up. M1 times the percent abundance of 1 plus M2 times the percent abundance of 2, and so forth and so on, equals atomic mass. Okay, now let's talk about this percent abundance here for a second. So this is what simply occurs in nature. If you took, for example, that carbon 12 and carbon 14, and you just took if you looked at all carbon in the universe, well, there's going to be some carbon 12, there's going to be some carbon 14, and there's going to be a ratio of what those two are. I don't remember exactly what carbon is. It's pretty close to mostly carbon 12. So maybe for carbon 12, it's 98% of all carbon in the universe is carbon 12. Carbon 14, maybe 2% of the carbon is carbon 14. So that's your percents here. 98% carbon 12, 2% carbon 14. These are called your percent abundances. Sometimes they're called natural abundances or relative abundances. There's just different ways you can call them. But it's basically just your percentages. I know that's going to be mostly carbon 12 because the atomic mass of carbon 12 is 12.01. So that's very weighted towards the 12. It's almost all 12 because it's only barely above 12. So there's very little of this carbon 14. It's probably less than 1% actually. And so that's actually a logic. You can do a logic check there. When you do your answer, hey, look, where is it weighted? Is it weighted in the correct direction? If it's not, you did some math wrong. Okay, so let's do a couple of example problems, and that will get you on your way. This looks like I think it's cut off at the top here. So it says, what is the atomic mass of an element that has 2 isotopes of the following composition? So isotope 1 has a mass of 23.9 AMUs, and that's 14.7%. Isotope 2 has a mass of 24.8 AMUs, and that's 85.3% of the isotopes. And so we'll use our little equation that we produced. Mass of 1 times percent of 1 plus mass of 2 times percent of 2 will equal our atomic mass. And so looking at the mass of 1, that's going to be 23.9. The percent of 1, we move our decimal, so that's 0.147 plus the mass of 2 is 24.8 AMUs times the percent of that 0.853. Punch those into your calculator, and we'll get 3.51 here, 24.8 times 0.853 is 21.2, and we'll add those together, and we get 24.7 would be our AMUs. That's pretty straightforward. Let's do one more example that's a little more complicated. What is the percent abundance? How do we find the percent abundances? Well, same equation, M1 percent 1 plus M2 percent 2 equals the atomic mass. Okay, and so we're just going to plug in. So percent abundance of the isotopes of silver, we have a mass of 106.8. We don't know what the percent is though. Mass of 2 is 108.8. Again, we don't know what the percent is. We're looking for those percent abundances. But we do know what the atomic mass of silver is. It's 107.8682. So here's the deal. Percents add up to 100. And so whatever the percent here is, if we make this percent 1, I'm going to erase that. If we make that X, well, this X plus this one must equal 100, or in percent and in fractional decimal format equal 1. And so if we erase this one over here, this must be x1 minus x, because x plus x equals 100%. The 2% equal 100%. And so this will give us our percent. There's a little bit of algebra there for you. So now you're just going to do your algebraic solutions here. So 106.8 times x is 106.8x. 108.8 times 1 is 108.8. And then 108.8 times x minus 108.8x equals 107.8682. Group your like terms, 106.8 and negative 108.8 is negative 2x. And 107, let me do this real quick, 107.8682 minus 108.8 is negative 0.9318. And then if we will divide by negative 2, we will get x equals to 0.4659, which equates to 46.59%. So and that's x, which is this, which corresponds to that. And so it is 46.59%, silver 106.8, which means the 108.8 is the other half, or the other portion. 100 minus 46.59, or 53.41. So 53.41%, 108.8. And so that is how you can find the percent abundances. If you don't know the percent abundances, you can do it that way. So just using x and 1 minus x as your percents, because they will total up to 100. Okay, guys, have a good day. Practice your worksheets, practice your practice problems. Come see me if you have questions about how to do these, but they should be pretty straightforward once you look at the examples. You may have to rewind and watch them again, but you should be able to get those pretty good. See you later.